Hello everyone, this is Dr. Webb. Over the last couple of videos where we were working on vector functions, we were doing calculus on one-dimensional objects, curves, which meant that the work that we were doing was still very similar to the work you did in one-dimensional calculus in Calc 1. A lot of the ideas were exactly the same. There were some changes when because we had things curving around in three-dimensional space and we were using things with vectors, but deep down, morally, we were doing the same kind of work. Now in this video, we're going to be changing gears quite significantly. So now we're going to be talking about multivariable functions. So these are functions where the input is no longer one-dimensional and now it's going to be two or more dimensional. And so what that means is that while at times some of the calculus we're going to be doing will seem similar to what we've done before, at other times it may be significantly different. So let's start off talking about functions of two variables. Right? So what we're talking about here is that now instead of the input being one variable, like x from what you remember from Calc 1, or t when we were talking about vector functions, now the input is going to be two variables, usually x and y. So a two-variable function, f of xy, is going to take points from the xy plane as input, and it's going to spit out real numbers, right? And so sometimes the more mathy way of writing this is saying our function f of xy is going to take two variables and use those two variables to end up with something with one real number, right? So the input is going to be x and y, and the output usually will use something like z coming out of it. So two values go in, one value comes out. Okay, and so for these functions we have the similar concepts that we had for one function, one variable function. So we can talk about the domain, but now the domain is going to be subset of the xy plane, right? So it's going to be a set of points x and y together where the function can be evaluated. The range is still going to be very similar to when we had y equals f of x. It's just going to be the set of values in R that the function can take. So let's think about this by doing an example. So let's let f of xy equals square root of xy times the natural log of 2x minus 3y divided by x squared minus y squared. And so what we want to know is what are the values x and y that we can plug into this and make sense out of this function. So we have a lot of different things going on here. So let's break these up bit by bit. So 1, we're multiplying by square root of xy. 2, we've got a natural log of 2x minus 3y. And finally, we're dividing by x squared minus y squared. So let's treat these all separately. Okay, so we've got square root of x times y. Well, when does that make sense? When can we plug things in and take the square root of them? Well, we're allowed to do that whenever, with real numbers, whenever their product, x and y, is going to be greater than or equal to 0. We're allowed to plug in non-negative things into square root. So this is going to make sense whenever x times y is greater than or equal to 0. Well, when is x times y going to be greater than or equal to 0? Well, if they're both non-negative, that's certainly going to be true. Right? So if they're both non-negative together, you're multiplying two positive things together, you're going to get something greater than or equal to 0. But also if they're both negative, right? If they're both negative when you multiply them together, then that's also going to make sense. And also the axes are on here. You're allowed to take the square root of 0. The square root of 0 is 0. And so this is going to be the domain for just this part of the function. right? Well, so what about natural log of 2x minus 3y? Well, for ln of 2x minus 3y, well, what are the restrictions of plugging things into natural log? Well, you have to plug positive things into natural log. You can't even plug in 0. Natural log only takes in positive values for its domain. And so that means that we need 2x minus 3y to be greater than 0 for this to make sense. And so this turns into we need 2x to be bigger than 3y, which is the same thing as saying 2/3 x is bigger than y. Right, so what's this going to do? Well, so 2/3 x equals to y. That's a line with slope 2/3. Okay, now which side of this line is going to be 2/3 of x greater than y? Well, you can kind of plug in values into here. So I think that if x is, say, 1 and y is 0, I think I can convince you that 2/3 is bigger than 0. And so then, since this is on the bottom half of that line, that's saying that the entire bottom half would be in the domain for that function. Okay. And then last but not least, we're dividing by x squared minus y squared. So since we're dividing, that means x squared minus y squared cannot equal 0. And so that means that x squared cannot equal y squared. Well, what does it mean if x squared equals y squared? That means x cannot be plus or minus y. Right? So this is really drawing out two lines. One, x is equal to minus y. One for x equals y. So we're not allowed to be on those lines, but you're allowed to be on anything else. Okay. So the blue here represents what the domain for square root of xy is. The red represents the domain for the natural log of 2x minus 3y. And everything except for these dotted lines is the domain for 1 over x squared minus y squared. And so if we want to talk about the domain of the entire function, it has to be where all three of these are defined at the same time. Okay, so where are all three of these defined at the same time? Well, one place, let's use green here. So one place, the bottom edge of square root of xy goes along the x-axis, and then it goes up along this line 2/3 x equals y, but it doesn't include that. And then this place right here is in all three. So that's part of the domain. What about on the other side? Well, it looks like I have that y-axis down there is going to be in all three. The red part ends right there, and I have to take out this dotted line right there. And so this part right here, taking out this dotted line for y equals x on that side, that's going to be in the domain, right? And so the total domain for this function is all of this green area here. Okay, and so this is the place where all three of those domains are satisfied at the same time. Okay, so it's a little bit messy, but this is what the domain is, and this is really how we treat the domain. It is a subset of the x and y plane, where each of these makes sense. Okay, so how do we graph a two-variable function? Well, the output, the range is going to be expressed in terms of z, and the inputs are coming from the xy plane, right? So if we have some value x naught, y naught, that gives us some point x naught, y naught in the domain. Well, when we plug this into the function, we're going to get some height out of this, and this height is going to be f of x naught, y naught. Right? And then we can kind of repeat this over everything in the domain, and so what are we going to get? Well, we're going to get a bunch of heights over the xy plane. Right? So the graph of z over equals f of xy, we're going to call this is a surface. Okay. What does being a function mean here? Well, we still have the vertical line test. It's just that the vertical line test now means that if you take any point on the xy plane and do a line straight up, it is only going to hit the surface at one point. It's not going to hit the surface twice. So it's the exact same thing as before, it's just now these vertical lines, you're allowed to move them around anywhere on the xy plane. Okay. So let's do a brief example of sort of thinking about how we would sketch a graph of the surface. Z equals 2x squared minus y. So this is a general idea on how to do it. It doesn't work for everything, but this gives you a good idea. So kind of what we're going to do is we're going to try and build kind of a wireframe for what this looks like. And so we're going to do this trying to break it down into sort of curves, getting rid of one variable in different ways. Right? So first thing I'm going to do is I'm going to think about what happens, say, on what's this going to look like on the xz plane. So on the xz plane, that means we're going to set y equals to 0. So if I set y equals to 0 here, I'm going to get z equals 2x squared. And so what's that going to be? So that's going to be a parabola pointing up on the xz plane. So up here, let's make that a little bit better. So up here, that's curving up on the xz plane. Same thing in the back, curving up on the xz plane. Okay, secondly, I'm going to think about what this looks like on the yz plane. And so now we're going to set x equals to 0, and this turns into z equals minus y. And so I can draw that on the yz plane. Right, so z equals minus y, so that is a line slope minus 1. So the red line is happening on the yz plane. Okay, now I'm going to sort of fill in what the horizontal ways look like. And so I'm going to do what are called level curves. And what we mean by a level curve is we're going to set z to be different values and then see what the curve xy equals looks like. Okay, so first let's start off with, say, setting z equal to 0. So we're looking at what we have on the xy plane. And so then if z equals 0, then we have 0 is equal to 2x squared minus y, which is the same thing as y is equal to 2x squared. Right, so that's going to be a parabola on the xy plane, going out like that. And like that. Okay. What about when z equals 1? Well, when z equals 1, we're going to have 1 is equal to 2x squared minus y, which I can rearrange to be y is equal to 2x squared minus 1, right? And so that's the same parabola we had before, but now it's shifted down minus 1 in the y direction. And so now, and it would be starting on this line, on the yz plane, and it's going to go horizontally and connect up with the parabola on the xz plane, and then continue to go out horizontally as a parabola. Okay, and we can let z be 2. This level curve would end up looking like 2x squared minus 2. And so we go up to 2. And similar to before, we have the same basic parabola going up above. Okay, and so if we kept on doing these wireframes, we keep having these parabolas coming out horizontally. Right, so what exactly does this look like? So on the xy plane, we've got this straight line, kind of like a straight back, going straight down. And then horizontally from there, we have these parabolas shooting out. Okay. And these parabolas are going through and hitting this this parabola, the blue parabola, z equals 2x squared on the xy plane, on the xz plane. Okay, and so the way to think about this is it's sort of like, kind of imagine that if you took a parabolic cylinder, so you took a parabola, a horizontal parabola, and just built that up vertically, and then pushed that over to its side, slanted it over so that its back was slanted, but you still have horizontally these parabolas going out. Okay. Okay, so now we want to do calculus, so we got to talk about limits of two variable functions. So in Calc 1, and when we were talking about vector functions, limits are not that bad, because if we're talking about limit of going to some point, how many different ways do you have to going to that point? Well, you have exactly 2, right? You can either come to it from the left, or you could come to it from the right. So this is the situation from Calc 1, right? Well, what now if you have a point on the xy plane? How many different ways on the xy plane can you come to that point? Well, you can come left and right, but you can also come up and down, sideways, everything like that. So there's a whole circle of straight ways you can come in. But even then, that's not really all the different ways you can come in. There's actually all sorts of different curves we can talk about that go in to that point. Right? And so this is infinitely more complex than what we had in Calc 1. Calc 1, when we were doing with limits, we had to worry about 2 things. What happens when you come to the left, and what happens when you come from the right. In multivariable limits, where you're coming into a point in 2 space, you have to worry about every possible way that you can get into that point. And so these are much, 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 much harder. So when we say that the multivariable function, or in this case a 2-variable function, has a limit as we approach a point, so here we're approaching the point AB, we're saying that limit equals L. What that means is that for any path, and so we're representing a path as a vector function on R2 to AB, and letting it hits AB when t equals t0. That means that on any path, when we plug in those components into f of x, we get that limit L. Okay? And so the important thing to notice here is that we're starting off here. This is a two-dimensional limit. The two dimensions are coming from x and y. In the limit on the bottom, when we've changed it into looking at a path, well, now we've really just changed it into, this is a one-dimensional limit. Right, and where the one dimension is coming from t. Right? And so even though we're plugging these in as the two different components, really, once you plug this in, the only variable going on in t. And this is the type of function that we're familiar with. The difficulty here is that we'd have to do this for any path. And so all possible paths into that point. And that's what makes it really difficult. Now, I should say that this is not the true technical definition of a two-variable limit that mathematicians use. To go through and do that true definition would take an awful lot more work. And usually it's reserved for, at least the essence of that is reserved for a course called Analysis that you would take as one of your final courses as an undergraduate math major. And so we are not working towards getting to that level of depth in understanding two variable limits right here. But this definition is equivalent and it's morally true. And so while it's going to be really, really difficult for us to figure out how to actually show that limits exist, this does give us a way to show how limits don't exist. Right? So how then, coming from this idea of all paths have to lead to the same value, how then can we show that a limit doesn't exist? Well, one thing that can go wrong is if we can find some limit where we can find some path where the limit doesn't exist at all. Right? So if the limit has to be the same value for all paths, well, then if we can find some path where the limit just doesn't exist, then right there, that's a counterexample. The other thing we can do is if we can find two different paths on the xy plane, both going to AB, where the two limits don't exist. Right? So we have a path 1 coming from x1, y1, and a path 2 coming from x2, y2, where we do those limits both going in towards the point AB, but those limits don't give us the same value. Okay, so let's do an example. Let's actually do a couple examples to show how this works. Okay, so in this one, we're trying to get to the point, we're trying to get to the origin, xy equals 0, 0. Okay, so we want to think about some paths we can do to get to the origin. Well, simplest path might be just go along the x-axis to the origin. We can even do it both ways, right? So if we're going along the x-axis, we're thinking about changing our x value and leaving our y value always at 0. So we're looking at the vector function here is t0, and we're looking at this as t goes to 0, and that's going to take us to 0, 0. Okay, so we can plug that in, and so we're looking at the limit as t goes to 0. Now everywhere where I see x, I'm going to plug in t, and everywhere where I see y, I'm going to plug in 0. So this is going to end up as 3t squared minus 2 times 0 over t squared plus 0 squared. And so you can see that this simplifies down to 3t squared over t squared. The t squareds cancel off, and we get our value for the limit along this path to be 3. Okay, well, what's another path we can take? Well, similar to doing along the x-axis, we can do this along the y-axis. So on the y-axis, we're looking at our function being 0t as t goes to 0. And so plugging this in, so now whenever I see x's, I'm going to be plugging in 0. Whenever I see y's, I'm going to be plugging in t. And so now I'm going to get 3 times 0 squared minus 2t squared over 0 squared plus t squared. So this is going to give me the limit t goes to 0 of minus 2t squared over t squared. The t squareds cancel off, end up with minus 2. So along the y-axis, it looks like the function's going to minus 2. But along the x-axis, it looks like the function's going to 3. These two don't match. And so since for the limit to exist, it would have to match on all paths. We found 2 paths where they don't match, and so that's enough to show the limit does not exist. And we're done. Okay, so now let's look at this function. So we're looking at the limit of xy goes to 1, 1, 1 of 1 minus x times 1 minus y divided by 1 minus xy. We want to show this doesn't exist. Okay, and so here the point we're going to is 1, 1. So let's start off trying the same trick we did before. Right, so I'm just going to go and horizontal path. And so in this horizontal path, I can think about it as being t comma 1. I'm keeping my y value, my y component as a constant 1. And in this case, we're letting t go to 1. And so if we plug this in, x, y, let's do this in terms of t. T is going to 1. So I'm going to have 1 minus t times 1 minus, for y I'm plugging in 1, so I end up with 1 minus 1 there, over 1 minus t. Well, 1 minus 1, that's giving me 0. And so this is going to be 0 the whole way across there. Right, so this equals, so this one right here is going to equal 0. Similarly, if we go along a vertical path, so we're thinking about, now we're thinking about 1t, this is going to turn into, well, now in the 1 minus x part's going to turn into 1 minus 1 times 1 minus t over 1 minus t. And so that's going to give me 0. Right? Well, is there anything else I can do? Well, I can go along, say, actually, you know what? The path I'm going to go along now, this is going to seem a little bit funky, but I'm going to show you how this works. I'm going to pick the path for my third one along t comma 1 over t. Right? And so this is going along y equals 1 over x. And we're going to be doing this as t goes to 1. And so this path is kind of coming through like that. So it's actually approaching it not in a straight line, it's approaching it along a hyperbola. Well, what happens when we plug this into here? So we're looking at the limit as t goes to 1, 1 minus t times 1 minus 1 over t. And then in the bottom, we have 1 minus t times 1 over t. Okay, so t is approaching 1, but t is not at 1. So this top here, these are going to be two non-zero numbers. So this top here is not 0. Whereas on the bottom, we have 1 minus t times 1 over t. Well, what's t times 1 over t? That's 1. And so on the bottom, we have 1 minus 1, which is 0. And so not only does this limit not exist on this path, but the function on the bottom, this whole function is not defined along this entire path. So on this entire path, the function is not defined. And so if it's not defined on the entire path, then there's no possible way to take a limit on it. So this means the limit does not exist. So even though when we did the limit along the horizontal and vertical, we both got the same thing, 0, 0, that was not working. That only showing two paths. We really have to show that it's true for all paths. And so we were able to find a path where the function is not defined. And so if the function is not defined there, then that means the limit does not exist. Okay, so now that we at least have some handle on the idea of what a limit is, even though we're not really going to be showing very often that limits actually do exist, we still can talk about what continuity means. And so continuity is going to be the exact same idea. We're going to say a function is continuous at a point a, b if the limit as you approach is the limit of the function as you approach a, b is equal to the function's value at a, b. Okay, and for our purposes, we're just going to assume, so for us, in almost all respects, our functions will be continuous whenever they are defined. Okay. And so in general, the general fact that we're going to use, we're not going to prove, is that rational functions of x and y are continuous when defined. And so if you think back about the last two examples, they were rational functions, but we were looking at limits at places they weren't defined. And so that's why we were able to get show that the limits don't exist there. But if we were to pick any values of x and y where the function was defined, at that point, those functions were going to be continuous. And so the result of this, if we just have rational functions of x and y that are, so they're continuous when they're defined, so essentially when you're not defining 0, what the offshoot of that is that then if you plug in continuous functions into a rational function of x and y, those are going to be continuous wherever they're defined. And so pretty much since generally that's the type of functions that we're always going to be looking at in this course, if you have a function that looks like it's continuous and it's getting plugged into some way, and we're looking at a point where the function is actually defined, we are just going to assume that it's continuous there. Okay, so the title of this video was multivariable functions, and we've really only been talking about functions in two variables, So what about if we're dealing with functions with 3 or more variables? So a function with 3 variables would look something like w is equal to some function of x, y, and z. And so now here, our domain is part of 3 space. Right? So we're taking things, points in 3 space, and then assigning them some real value. Or we could keep on going higher than this. We could talk about functions of x, y, z, and w, etc., more and more variables. The ideas for everything that we've been doing is pretty similar. Drawing a function in 3 variables, w is equal to f of x, y, z, that's really difficult. It's really hard to make. It's hard enough to make 3-dimensional pictures. I'm not even going to try to make 4-dimensional pictures, partially because our brains can't even fathom what they look like. Usually, if we want to represent a function in 4 variables graphically, we will pick, different values of w and look at what the surfaces are that give you that. And so we break it down into, rather than trying to show all 4 dimensions at once, we for one of the dimensions we pick a constant and then look at what happens in the other 3. So graphing for 3 or more variables, that's its own beast. And the main limitation there is the limitations of our own measly human brains. Whereas the other ideas, such as for limits and continuity, that's pretty much exactly the same, or completely analogous. The big jump for limits is going from 1 variable, where you're only worrying about 2 directions going in, to 2 variables where all of a sudden you have infinitely many. Now when you have 3 variables, you still have infinitely many, and you're still talking about all the possible paths in 3 dimensions getting there. And the definition for continuity is going to be exactly the same. And so whenever we need to do stuff for 3 or more variables, the basic ideas, ways that we use things from 2 variables is still going to hold true here. So that is all I have for you for this video. I will see you again later.